Hi Chemistry, Mrs. KJ here, going over 4.02, Measuring the Flow of Heat. Heat is the movement of thermal energy from one place to another. Since the 18th century, scientists have analyzed data showing how objects can be heated and cooled and how heat can flow from one object to another. However, it wasn't until the 19th century, when the nature of the atom was discovered, that scientists knew what the nature of heat was and how it was transferred from one object to another. In this lesson, you'll be introduced to the concepts of thermal energy, heat, and heat transfer. Goals for the lesson: explain heat in terms of molecular energy, explain that heat always flows from warmer to cooler objects, describe the motion of molecules in heat flow, contrast thermal energy, heat, and temperature, define calorie, abbreviated lowercase cal, and joule, abbreviated capital J. And then if we look at our diagram, thermal energy transfer is called heat. It flows from hot to cold. Thermal energy is measured as temperature. Thermal energy is indicated by molecular motion. And on slide 2, you can get the student guide. And from the student guide, I kept the beginning paragraph, the goals from the lesson, our keywords and pronunciation. Calorie is the amount of thermal energy it takes to raise a gram of water 1 degree Celsius at normal atmospheric pressure. So if you have 1 gram of water and you want to increase the temperature exactly 1 degree Celsius, that's what a calorie is. Heat is a form of energy transferred by way of conduction, convection, or radiation by virtue of a difference in temperature. Heat is energy in transit, so it has to be moving. Heat is energy flow measured in energy units. We have a joule. Joule is the SI or Système International or metric system, derived unit to measure energy, work, and quantity of heat. For work, a joule is the amount of work done by a force of 1 Newton acting through 1 meter, also called a Newton meter. So in other words, we're going to say we have 5 joules of heat. Thermal energy is the energy of movement of groups of ions, atoms, or chemical compounds. And as you can see from the picture, which I put in here too, heat and temperature are different. Okay, so that's important, where in everyday life we kind of use them interchangeably, but in chemistry there is a distinct difference that we need to be aware of. Ice cools a liquid. What happens when you make a glass of ice water? You pour liquid water from the tap into a glass and add an ice cube. The water gets colder and the ice eventually melts. That is, the ice gets warmer. At first guess, you might think something was transferred from the liquid to the solid, but what? This question and similar questions about heat transfer perplexed scientists in the 18th century and early 19th centuries. They knew that heat flowed from hot to cold objects, but not the other way around. But what was heat? Before the nature of the atom was discovered, scientists thought that a weightless, invisible fluid called caloric made objects either hot or cold. They believed that hot objects had caloric, while cold ones did not. In 1783, Antoine Lavoisier proposed that caloric moved from hot objects to cold objects. What the highly intelligent Lavoisier lacked was knowledge of the particulate nature of matter. In other words, he needed to know about atoms. In 1824, Sadi Carnot explained how heat engines or steam engines worked based only on the caloric theory that prevailed at the time. Carnot's theory also attempted to explain why ice would not warm water. According to his theory, ice would not warm the water because it did not have as much caloric as the surrounding water. So of course we know that there's not this caloric fluid anymore, but we do still know that heat travels from hot to cold. All substances have thermal energy. As you might recall, all substances have internal energy. This internal energy is also called thermal energy or internal kinetic energy. The thermal energy of a substance is the combined motion of all the particles within. This thermal energy is measured by measuring the temperature of the substance. The temperature represents the average kinetic energy of all the particles within the substance. So in other words, if we take a look at how fast the atoms are moving, that is temperature. At high temperatures, particles move rapidly, while at low temperatures they move slowly. By particulates, we mean ions, atoms, molecules, ionic compounds, and other atomic level particles. All right, so the fact that these are colliding more often and moving faster results in a higher temperature. So thermal energy is due to the motion of molecules. So I added to our notes, all substances have thermal energy. This internal energy is also called thermal energy or internal kinetic energy. Remember, kinetic means motion. The thermal energy of a substance is the combined motion of all the particles within it. Thermal energy is measured by measuring the temperature of the substance. The temperature represents the average kinetic energy of all the particles within the substance. In other words, how fast the molecules are moving. Faster equals warmer equals a higher temperature. Heat is the transfer of thermal energy. Consider the two compartments with liquids at different temperatures that are in contact. Play the animation to see how heat moves. We measure heat by measuring a change in temperature. So the left compartment is going to lose heat or it's cooled, while the right compartment gains heat or is warmed. We recognize this by the change in temperature. So heat is measured as transfer of thermal energy. So again, we can just see that the temperatures in each move, the thermometers move until they are even, until they're at equilibrium. So heat's going to go from hot to cold until both are the same temperature or have the same amount of heat. So heat is the transfer. That's very important. It's the transfer of thermal energy, and we measure heat by measuring a change in temperature. And then, so the left compartment lost heat, was cooled, while the right compartment gained heat, warmed. We recognize this by a change of temperature. Collisions of molecules transfer thermal energy. On the left side, molecules, for example, collide with the barrier and transfer energy, causing barrier molecules to vibrate faster. After each collision, the left side molecules move more slowly, or the temperature decreases. On the right side, molecules collide with the barrier molecules. After each collision, the right side molecules move faster, or temperature increases. When equilibrium is reached, the molecules in each compartment and in the barrier move at the same rate, and the temperatures are equal. Okay? So you can see the molecules from the left side are going to hit the barrier. It causes the barrier to bounce, causes the other barrier to bounce. When a molecule from the right side hits it, that molecule starts moving faster. So now this one's moving slower. The energy's in the barrier. Boom. The energy's in the molecule on the right-hand side until molecules all over have the same amount of energy, which means that they are going to have the same temperature. We'll just add that to our notes. Heat transfers in a glass of ice water. Think again about the ice water example. How does heat transfer here? Okay, so our ice molecules are negative 20 degrees Celsius, move more slowly than water molecules, which are at positive 21 degrees Celsius. All right, so we got some water down here. We have the ice up here. Fast-moving water molecules collide with the ice crystals. Okay, so they're running into each other, and when they bump into the ice, they make those ice molecules move faster. So it transferred thermal energy to the ice. The ice crystal molecules vibrate faster and the ice temperature increases. The water molecules move more slowly because it gave some of its energy to the ice, and the water temperature decreases. As the ice crystals vibrate faster and faster, they eventually break apart and melt into liquid water. The melted ice and the surrounding liquid reach the same equal temperature that's between 0 degrees Celsius and 21 degrees Celsius. Why does it have to be at least 0? Because we're saying that it all melted, and so water melts at 0 degrees Celsius, and obviously it can't be warmer than 21 degrees because that's how warm the water is. Assuming, of course, that the outside temperature here is not playing a huge part and that this burner, which kind of throws in a whole nother loop. I don't know why they put it on a burner. I guess to show that they're adding more heat in order to melt the ice. Thermal energy, temperature, and heat are not the same. Here are the difference between these terms. Thermal energy. the internal kinetic energy of all the particles in any substances. So the fact that atoms are constantly moving, that's thermal energy. Temperature, the measure of the thermal energy within any substance. Temperature measures the average kinetic energy of the particles in the substance. So how fast or how often they're bumping into each other. Heat, the change in thermal energy of a substance. Heat is measured by a change in temperature. Temperature increases, heat is gained. Temperature decreases, heat is lost. So I'm going to copy paste that entire slide because, like I said, people tend to really get these definitions mixed up. And the reason, of course, being that we use temperature and heat in everyday life. And so when we use words in everyday life and they have a different meaning in science, we really got to make an effort to make sure that we know that. All right, so heat transfer experiment. Place the hot container next to the cooled container. And particle view, we have our molecules moving. They should be moving faster on which side? The left side, because they had more energy. And it took some of that energy when the particles bumped into the edge of the container, and that caused the energy to go to this container, which caused it to go to these molecules, which in turn will make them go faster, which, I don't know, it's kind of hard to see. I feel like it's kind of skipping a lot on me, but we definitely should be seeing that this is moving faster than the other side. All right. How well do you understand heat transfer? Look at the top illustration. The beaker on the left is warmer than the beaker on the right. Which way will the heat move? Energy flows from high to low, so there's a net transfer of thermal energy through collisions from left to right. The heat will move from hot to cold because the molecules on the left will transfer energy to the slower moving molecules on the right. And they will continue to do that until, if you look at the thermometers, they reach equilibrium. So always go from hot to cold. Can you explain why ice does not heat a glass of ice water? In the ice water, the ice is a lower temperature than the water. Therefore, the ice crystals move more slowly than the water molecules. When the water molecules collide with the ice crystals, energy is always transferred from the faster moving molecules to the slower moving molecules. It never happens the other way around. The thermal energy is transferred from the hotter object, water, to the colder object, ice. Never the other way around. Do you get that that's a key point since they keep saying it? High to low, warm to cold. So the ice will melt in the water. You will never see the ice get colder and the water get hotter. Okay, so my water molecules are moving around and my ice molecules are simply staying there they are still moving. I don't know why it's not letting me show you this. They are still moving, but they are just vibrating back and forth. There we go. Versus when they are water molecules, they're moving all over, and the water molecules give some of the energy to the ice crystals, therefore causing the ice to melt. How do we measure how much heat is exchanged? Heat is the transfer of energy and is measured by a change in temperature. But how do we express how much heat is exchanged? There are two units that scientists frequently use. The calorie with a lowercase c, that's really important, is the amount of heat it takes to raise 1 gram of water by 1 degree Celsius. So if you had 1 gram of water and you made it go from 55 to 56 degrees Celsius, that took 1 calorie of heat. Or a joule, 1 calorie is equal to about 186 joules. Typical amounts of heat in many heat transfers are on the order of thousands of calories, or kilocalories, or kcal, or thousands of joules, kilojoule, or kj. Yep, I know, my favorite, kj. For example, when you heat 8 ounces of water from room temperature, 21 degrees Celsius, to boiling, 100 degrees Celsius for tea, you must add about 18.7 kilocalories, 1,000 calories, or 78.3 kilojoules of heat to the water. So this is just a thermal image. You can hit pause and look at it. Here is the last part to review. Go ahead and hit pause and add this last review part to your